Okay, now let's talk about machine learning workflow, which means when we have actual project, machine learning project, then what kind of process do we have to follow? Okay, so first, when we start a project, then the first thing is to gather and collect data samples. Okay, that is data acquisition, and data is collected, gathered from various sources like sensors, activity trackers, and social media platforms, and experiment surveys, etc. There are so many different various sources. Okay, actually, in machine learning class, we have not so much to talk about data acquisition. So let's assume that you have data set. But in practice, it will take a lot of time to collect the data samples. And next step is preparation, where data is cleansed and pre-processed, okay, and eventually becomes a data set. So it includes lots of things like removing errors, mistakes, duplicates, and inconsistencies in data. And also, we have to annotate data samples, and we have to combine some data samples from different sources. And sometimes we have missings in our data samples. Like when we get one sample, then some features are missing. In that case, we can delete that sample, or we can do something about the missing values. And the next one is analysis. So analysis is to understand data better. Okay, so data is evaluated, and we actually check some samples. We actually visualize some of them to understand the data samples. And actually, these processes are not clearly distinguishable sometimes. Sometimes, the boundary between these processes are quite blurred. Okay. The next one is modeling. So data is patternized and generalized as models. So models can explain the general patterns that are frequently observed in data. And models are often used to make predictions or inferences. So most of the time in this semester, we're going to talk about analysis and modeling, and sometimes preparation, and a little bit about visualization too. And in visualization, data is visualized to provide intuitive overview. In analysis, we have visualization, and after modeling, after experiment, then we have a visualization too. And the last but not least, we have deployment and maintenance. So when we have a project, actual project, then we get the data from a company or from somewhere, and we build our model, and we train the model, and we actually evaluate the performance, and that's pretty much it. But if it is an industrial project, then we have to deploy the algorithm, the model, into the real system. When we deploy, there are a couple of more issues there, and after deploying, then we have to think about the maintenance. Okay, so these are completely different kind of areas. So in this class, we don't care this deployment and maintenance. Okay, then next one is components of machine learning. It's pretty much similar to workflow, but in a little different perspective. Okay, so if someone is working on machine learning, then he is working on one of the followings. Okay, so first one is data. Then we have to gather data. So it's actually corresponding to data acquisition process. We have many different kinds of data. Okay, so we have features and labels, and data could be sequential, and it has special format. Okay, and then data can be split up into training data and validation data and testing data. And once the data is done, then we have to think about the models. There are many different machine learning models like SVM, neural network, and light Bayes and Bayesian network, etc., etc. So we have lots of machine learning models. And then once the model is fixed, then the next one is objective function. So we have to choose one of these objective functions. Usually, if it is a classification problem, then cross entropy is the most popular objective function. If it is a regression, then RMSE or MSE. Or if it is a probabilistic model, then likelihood or posterior would be the objective function. And if it is automatic speech recognition, then word error rate is the objective function. And if it is machine translation, then the blue score is the objective function. So depending on the application or scenario, then we have to choose a proper objective function. Now we have data and the models and objective function, then we have to actually train. We have to choose one of these optimization techniques. Then with one of them, we have to train this model. Okay. Then as I said, this selection, our choice depends on application scenario. Is it classification problem, or do we have to reduce the dimensionality, or do we have to estimate some specific values, or do we have to recognize some things? So depending on these kind of scenarios, then we have to choose one of them. If it is a speech recognition system, then we need the features, and the data is sequential, and we need the labels, and we have to split the data samples into 3 different categories, and the models could be neural network and WER, and the gradient descent method can be used, something like this. Okay, let's talk a little more about data in machine learning. Okay, so data is actually the key ingredient of machine learning. And as I said, the data can come from nature or user behavior or industrial process. So there are so many various resources. And it could be structured, it could be unstructured. So if it is a structured, then you can have this data as a matrix or tensors. Okay. So for example, in movie review, then we have a structured data and unstructured data. So in movie review, we have some numbers about these stars. Is it 4 or 5? So if we have some specific number, then this one is a structured data sample, data value. And the unstructured is something like a text, okay? And the plot was great, and story was beautiful, but the actress was not great. So this kind of text is unstructured. Okay. And usually the data is messy, and the cleansing and preparation is really a time-consuming job. And probably you will spend like 90% of your time in data cleansing and preparation. But if you have to increase the performance of your system, then you have to focus on data samples. If you clean up the data more carefully, then you can increase the performance quite easily. Okay, but in this class, then we don't talk much about this kind of process, even though this one is more crucial than proper modeling or training. Okay, next we have a couple of different categories in machine learning algorithms. First one is unsupervised learning. In this case, we have input X, but we don't have label Y. So we have X, but we don't have Y. And we have supervised learning. In this case, we have X and Y. So in this case, most of the time, we want the relationship between. We want to know the relationship between X and Y. More specifically, we want to map X to Y. Okay, and the next one is semi-supervised learning. Okay, semi-supervised learning is kind of in the middle of this unsupervised learning and supervised learning. So some data samples have X and Y, but most of the data samples don't have Y. Okay, so in that case, we have to think about the semi-supervised learning. And even though in practice semi-supervised learning is really popular, but in theory in the textbook we don't have this that much. Usually in textbook we have unsupervised learning and supervised learning, and reinforcement learning is completely different. So usually in machine learning we have unsupervised learning and supervised learning in the textbook. Even though reinforcement learning is a part of machine learning, but reinforcement learning is way much more complicated than these guys. Okay, first, unsupervised learning. As I said, in unsupervised learning we don't have why. Okay, we have only input, we don't have label. Then what can we do only with x without y? So the clustering is one of the most popular example of unsupervised learning. So given some samples, we want to categorize these samples. And the dimension reduction is another one. So when we measure some data sample, then it has a lot of features, like 1,000 features. Too many features we have, then we want to reduce the dimensionality to extract some important features. So these are two important examples of unsupervised learning. So in this semester, we are going to learn a couple of algorithms of unsupervised learning. And next one is the supervised learning. And the supervised learning is really popular because when it comes to machine learning, many people might heard about the face recognitions or image recognitions, right? So this recognition is one of supervised learning example. Recognition is actually classification. So classification is finding a boundary between the two different classes or three different classes. And the regression is also a supervised learning algorithm, but regression is a little bit different from classification. So in regression, we want to find the relationship between x and y. Okay, so we want to find this kind of line or some curve. Okay, so classification and regression, these two are the most popular examples of supervised learning, but they are different. And the last one is reinforcement learning. Okay, so in AlphaGo, they used the reinforcement learning algorithm. Actually, for the first time, AlphaGo was based on supervised learning, and they used reinforcement learning to train further. Okay, and then self-driving car can be trained based on the supervised learning or reinforcement learning. Okay, so when we talk about supervised learning or reinforcement learning, so we are not talking about the model. We are talking about how to train the model. Okay, so in AlphaGo, for example, we have the same model, but we train the model with the supervised learning and the reinforcement learning. And likewise, we can train machine translation with reinforcement learning technique. Okay, then what is the difference between reinforcement learning and supervised learning? So first of all, we have agent here and environment. In supervised learning, we have an agent or model, but we don't consider the environment in supervised learning. But in reinforcement learning, we have an environment. There are two major differences between the supervised learning and reinforcement learning. The first one is that in reinforcement learning, when agent make an action, then it changes the input to this agent. In supervised learning, when the model makes some prediction, okay, prediction corresponds to an action here. So when it predicts something, it doesn't make any difference to the next input. Okay, next input is fixed already. In supervised learning, something like image recognitions. When I recognize a tiger at this moment, then what is the next image? Current image has nothing to do with the next image. Okay, and then current prediction has nothing to do with the next image because next image is already fixed. But in reinforcement learning, the current action changes everything. Think about self-driving car. In self-driving car, the action is something like steering the wheel, okay, or accelerating, or pushing the brake pedal. So if we do something, then our next input will be different. If we steer the wheel to the left, okay, then we can see the next side of this road. Or if we turn to the right, then we are gonna see the right side of this road, okay? So the input will be affected by my current action. That's one major difference. And another difference is that agent cannot get the target label, but it gets just reward, not the target label. Let's say we have a multiple choice problem here, okay? Then if it is supervised learning, then when I predict one answer, when I say, oh, the answer is B, then if it is supervised learning, then it says it is correct or it is not correct. When it is not correct, then it says, oh, it is not correct. Actually, the answer is D, or like that. Okay, but if it is reinforcement learning, it's a little different. When I make a prediction, like, oh, the answer would be a B, okay, then we don't get the label, but instead we get a reward, like, oh, that is a good choice, or oh, that is a bad choice. Anyway, reinforcement learning is slightly different from supervised learning, but actually it is way much more complicated than the supervised learning. So we are not going to cover that in this semester probably. And before going into any other topics, then I think this is perfect moment to talk about discriminative and generative models. Okay, discriminative models are like a supervised learning. So we have X and Y. In this slide, it is T. Okay, so we have X and T. And discriminative model try to predict the target label T. So given X, we want to model T. So it means we want to find a mapping from X to T. Okay, so think about the classification. So we have if it is an image classification, then the input is image and the output is one of classes. Like, is it lion or is it tiger? Is it bear? Something like that. So we are interested in the mapping from X to T. And discriminative models are focusing on decision boundaries like a classification. Okay, so we're interested in this kind of boundary. Okay, and then it is not applicable to unlabeled data. So we're interested in supervised learning. But generative models are a little different. So we're interested in P of Tx or P of x given T. So basically, we are not interested in the labels, basically. Something like this. So we are interested in the distribution of x or x and t. Okay, so we focus on modeling each class's distribution, or if we don't have label, okay, then we focus on the modeling just x. If we have a multiple classes, then modeling each class's distribution. Okay, so it is applicable to unlabeled data like this. If we have unlabeled data, then it is something like just one class. Okay, we can use this one as an unsupervised learning, but at the same time, we can apply this one for supervised learning, like this. For classification with large data set, discriminative models have better performance, obviously, because if it is a classification, then discriminative models are better. But when we use generative models for classification, then we can use in this way. This is one example of generative models. This one is an example of discriminative models. Discriminative model are interested in this probability, P of zebra given data or P of no zebra given data. So data is given, X is given, then is it zebra or not? So T is zebra or not, right? So based on this probability, P of zebra given data is higher than P of no zebra given data, then it is a zebra. Otherwise, it is not a zebra. But in this case, if we use generative models, we are interested in modeling P of data zebra or P of data no zebra. So these ones. And when we compare these two probabilities, then if this one is higher than the green one, then we say, oh, this is a zebra. Otherwise, this is not a zebra. Okay, so we can use generative models for classification. Okay, but here's the thing. When a data set is large enough, then definitely discriminative models are always pretty much better than generative models. But when we have a large data set without the labels, okay, so we have a lot of data samples, X. We have a few data samples with X and T. So we have some data samples and we have large data set, then these generative models could be better than discriminative models, even though this one is a classification problem. Okay, so you don't have to understand everything here. Okay, we're gonna get back to these problems later. Okay, so this is just the introduction of machine learning chapter.